Here is a tutorial video for how to run light-off curves in the Reactor RGA system. And today I'll be showing you an N2O light-off curve. But instead of nitrous oxide, this method could be adapted to whatever reactant is being put into the reactor next. If you refer to the kinetics videos, you'll find that the initial steps all the way up into the light-off curve itself are the same as the kinetics video. So I will link to that. The key difference is that when we're cooling the reactor, we're not cooling it to 210 degrees, we're cooling it to less than 60 degrees, which means instead of turning the variac, I believe it was at 40 volts, it's going to be set to 10 volts. And then cooled. And then the fan will be turned off once we reach 60 to 65 degrees Celsius, and we'll just continue with the conditioning and the rest of the test. If you get to the end of the test, the first sample point is supposed to be at 40 degrees. And so if we get to the end of the conditioning and we're, say, at 45 degrees or 43 degrees, and you don't want to wait the last 30 to 60 minutes for it to cool down, you can just use 50 degrees as your first sample point. So there's not a lot of time commitment that's really given to those initial steps. Most of your time will be done or will be given to the light-off curve itself, where you have to sit and watch the temperatures and then change the variacs at specific points. We'll go over that a little bit later, but it's not until the last 2 hours where we're really giving a lot of effort ourselves. Altogether, the test will take about 8 to 9 hours total, and a lot of this has to do with the amount of time that you dedicate towards the cooling process, or if you forget to change the variac during the light-off curve itself. All right, it's been about 50 minutes since the pre-treatment ended. What I did was I turned off the variac and then set it to 0, and then I turned the fan on for the next 50 minutes. So I've since, I was at 55 degrees, so I've since turned the variac back on. I set it to 10 volts, and I have already started the bypass procedure in purging the lines and turning the RGA on. All this is the same as it was in the N2O kinetics video, so again, you can refer to that, and we will come back at the end of the 1 hour conditioning. As promised, we are back after the conditioning is finished, and I have already gone through and purged the reactor and done the calibration of the RGA. You can see that our temperature is now 38.2, and it's been stable there for about the last 20 minutes. This is a reading of 10 on the variac, so it's the same setting as before. And right now our flow conditions are the same flow conditions for the first sample point. So this is our setting for 26.5 milliliters per minute of N2O, 43.5 of helium, and this is approximately 5 for hydrogen. So if we look at the calibrations, this is the data sheet for the light-off curves. And I have a section here for the calibration. You want to take 3 points. So 2 of those points should be familiar from what was done in the N2O video. Since we have 26.5 mils a minute, we did the calibration point at 16.3. You also want to take a calibration point when you turn off the N2O and make up the difference with helium. So it was 70 for helium and 5 with hydrogen. And that's because you want to know where roughly where 100% conversion takes place, or when you've decently approximated it. So it's a bit of an oversight on my part. I don't have a time here. I'll have to add that into future printouts. But I usually test these in this order for the calibration. You can do it in a random order, but I think it's most beneficial that the sample point itself, or at least the sample flow rate that we're going to use for the test, the same one that we use for the conditioning, is the last point, because then we just get to turn the bypass and start the test. So you see that I have marked down the signal for 44 M over Z, mass over charge. So I'll take the point right now for this last point, because we can see that the N2O signal has stabilized. So we're at 59.88 seconds. This just changed over, but it's going to be, we'll pull off the data file itself. It's 8.38 to the minus 11. And you also want to record the reading from the pressure gauge for the vacuum system, so 478 to the -6. We're going to keep track of that during this test. It gives us a way to approximately correlate the signal drift of the N2O with the rise of the overall vacuum pressure in the vacuum system. So I'm going to initiate the test right now by flipping the bypass and then setting the variac voltage to 30. So we'll do that right now. And this is the same as it was before in the kinetics video, where we open up this valve and look for, yep, lots of gas coming out, so it held pressure. And now we have our reactant flow going through the reactor itself. Go to the variac, and we'll set it to 30. So I'm going to watch the thermocouple readout, and when it reaches 40, I'll wait for this time here, this one right there, to refresh. And when that refreshes, I'm going to record the 44 AMU signal. And that will be, the time will be recorded here, the signal will be recorded here, and then I'll also record the overall pressure of the system. This is going to get very repetitive, so I don't feel the need to record my taking of every point, but this will start at 40 degrees when the temperature turns over to 40. When it reaches 90, I'll turn the voltage of the variac up to 35. When it reaches 130, it'll go to 42. When it reaches 180 degrees, I'll turn up to 47. And 220 degrees, I'll turn it up to 50. So this is approximately 1.5 to 2 degrees a minute. It's going to take between 3 and 5 minutes for the temperature to reach the next 10 degree gradation. In fact, this one's going up kind of quickly, so I can take the first data point. So there's 40. Wait for this to refresh. Still, yeah, there we go, 6152. 8.44. E to the -11. We can see that's a little bit higher than our calibrated value here, so we're definitely not reacting anything. Or if we are, it's very small. And then 4.88 to the -6. All right. I've gone through already and figured out which voltage settings will, or when we have to increase the voltage setting, such that we're not heating the reactor faster than about 2.5 degrees a minute, 3 degrees a minute. And when we turn it up is when we'd have to wait longer than 5 minutes to go up the next 10 degrees, in case you're figuring out for yourself. But yeah, you go through, you do all the sample points up to 250 degrees, and then you can stop. If you want to go up to a higher temperature, you can. I would not go above, let's say, 350 degrees on this heating tape, because then you risk burning it out. But then, much like the kinetics video, you're going to follow the same shutdown procedure as before, where you'll turn off the N2O and the hydrogen, and then flow 100 milliliters a minute of the helium through the reactor while the fan is on and cooling, and the variac is set to 0. At that point also, you'll close the vacuum, the valve for the vacuum chamber, and click acquisition stop on the RGA itself. All right, I'm going to get to this. This involves a lot of sitting and watching the thermocouple readout. This will take approximately 2 hours to reach 250 degrees. This is the labor-heavy part of this test before we can set timers and do other things, but this one really requires attention. Now, one of my future ideas for this system has to do with another a hookup for the RGA. So there is an option to collect data up here. You can see this auxiliary input-output. So if we can connect that to the thermocouple here, and then calibrate the signal so that it's reading the correct temperature, we could just set timers and then change the variac. We wouldn't have to mark down the temperature at the same time. Another option, and I'll speak of this while the temperature is going up, just hit 50. So another option is that we could get a vertical split tube furnace instead of and use that ceramic insulation. So is that 6316? 8.61. So we see the signal going up, but 4.87, and this one, yeah, it's stayed about the same. Not sure what that's about. We'll watch this throughout the test. But if we get a vertical split tube furnace that has a temperature controller on it, that would also be ideal for controlling the temperature, because then you could set your own timers when the temperature is supposed to hit a given point. Combine that with the auxiliary input-output, and that would be a fantastic way to automate the system. But, yeah, that's all for here. The rest of this is could be covered with what was in the kinetics video. And we'll come back later to show a video where we work up the data into my pre-existing spreadsheets.